Okay, the first topic that I want us to look at is intermolecular forces. And once we're done with that, we're also going to take a look at the chemistry of water due to its intermolecular forces. Now, in the previous chapter, we learned about the bonds that keep atoms together, and we focused on ionic and metallic and covalent. In this chapter, we're only going to be focusing on covalent bonding because that is what keeps molecules together. But we're not going to be focusing on covalent bonding in the terms of how the atoms bond. We're going to be looking at covalently bonded molecules and how different covalently bonded molecules can bond to each other to form solids and liquids. In grade 10, you did learn about the force that keeps liquids and solids together when you did the kinetic molecular theory. And you learned that energy is needed to overcome these forces before a phase change can occur. So, a couple of questions we need to ask ourselves then. Why does matter exist in a solid and a liquid form? And when we take a look at this chapter, we will clearly see it's because of these intermolecular forces that exist between the molecules. What are interatomic forces? Now that's very easy. Inter means between or in, and atomic means atom. So it's the forces between atoms, keeping atoms together and forming molecules. What are intermolecular forces? So intermolecular forces are in between molecules, keeping molecules together. Like for instance here on the right hand side where we have hydrochloric acid bonded to another hydrochloric acid by means of that intermolecular force. We also want to take a look at what the relationship between interatomic and intermolecular forces are, and we also want to take a look at what does this have to do with covalent bonding. Now, we're going to answer this question now already, because from grade 10 you learned that ionic and metallic bonds form massive macro structures just by bonding to each other. So ionic bonding can be between atoms, but it can also just continue with that lattice structure and bond a lot of these different molecules together. Same with metallic bonding, where covalent bonding cannot do this, and that's where our intermolecular forces come in. So very importantly then, we want to define intermolecular forces, and we want to say that intermolecular forces are forces that act between molecules. Now, if we can think back to what we did in the previous chapter where we learned how to indicate if a molecule is polar or if a molecule is non-polar, we can describe the actual polarity of the molecule. Now, if you look on the YouTube channel, I will do a separate video on a couple of examples just so you can learn again or revise again how to determine polarity of molecules. So, very importantly, just because a bond is polar, that does not mean that a molecule is polar. And the shape of the molecule actually helps to determine the polarity of that molecule. Remember from the previous chapter, our shapes of molecules are molecular shapes and the ideal shapes, so that you can revise that, because you need those skills to be able to determine polarity and then determine the intermolecular force. So if we take a look at something like hydrogen bonding to hydrogen, we have a rule that tells us that all diatomic substances will always be non-polar, because the bond between them is non-polar covalent, because hydrogen has an electronegativity of 2.1 and the other hydrogen also 2.1. So the difference in electronegativity is 0, and that makes it a non-polar molecule. Hydrogen chloride, the hydrogen is 2.1, the chlorine is 3, so that makes us a difference, or gives us a difference of 0.9, which means that yes, the hydrogen and the chlorine is bonded through a polar covalent bond, but the molecule itself is polar, because the chlorine has a higher electronegativity and it pulls the shared pair closer to it, making the chlorine side partially negative and making the hydrogen side partially positive. If we take a look at something like carbon tetrafluoride, just to revise that rule in the beginning, just because the bond is polar does not mean the molecule is polar. Carbon has an electronegativity of 2.5. Fluorine, with the highest electronegativity of 4, makes these bonds polar covalent. In actual fact, it's strong polar covalent bonds, meaning that the shared electrons will spend a lot more time around the fluorines, and this will be the case for all of them, making the entire outside of this tetrahedral molecule negative, meaning that it's a non-polar molecule, even though the bonds are polar covalent.